So you want to learn calculus. Well, you've come to the right place. In this video, I will cover all calculus concepts at a level students in early high school and possibly even earlier can comprehend. So you see all these symbols here right now, and I know that they look really frightening, but soon we'll learn them all and, well, you can brag to your friends. So without any further ado, let's get started. All right, first things first, let's talk about functions. So you can think of functions as processing machines. You have this big box, which is your machine, and then you put something in, you get something out. So, for example, I could have a special machine. I could have it be called the doubler, trademark, the doubler, and it's going to take in one input, it's going to give me one output. So let's say that I gave it the output, say a number 5, and you'll never guess what it does. It gives me 10. So, but I can also give it a variable. So rather than giving it a number, I can give it something like x, or I can give it t, or y, or a, or b, or n, or p. It really doesn't matter. So soon you'll realize that the variable name in a function, it really doesn't matter. And what this machine will do, what this function will do, is it will give me an output, which will just be 2 times that variable. So 2x, 2t, 2y, etc. So that is your function. But what I can actually have is I can have my machine take more than one input. My machine could take 2 inputs. It could take 3 inputs, or my machine could also give me more than one output. So rather than just giving me 1, it can give me 2 or 3 or 4 or 5, and really it can give me as many inputs and outputs as I want. And that is just a general function. Now, since us mathematicians don't really want to draw a big box every single time we want to use a function, we instead use a shorthand notation and write f of x. So these are the exact same thing. Now this is probably notation that everyone has seen before, and also likely notation that many of you have never used before. So then this notation is just the exact same as writing y is equal to something, this is the much more, common notation before high school. So just replace y with f of x and you're good. Now the reason why we use this notation is really just because of convenience. Have you ever met a mathematician? I've got to say, they are the laziest people out there, to the point where they will write, instead of writing implies, they're going to write the arrow instead. Or instead of writing because, they will write this. And so we developed this shorthand so we can basically easily work with functions without too much trouble. Like, for example, erasing this machine. For example, we could write a function of an independent variable, or we could change our independent variable. So rather than writing f of x, we could write f of t, or we could write f of 2x, or we could write f of g of x, which this right here is its own function, and what this means is that you just give me the value of g of x, and then give me the value of f evaluated at g of x. So really these are the same thing, but here g of x is just 2x, right? So the way that we can think of this last one is just think of it as just another machine, right? We have one machine. This is going to be our machine, which is g of x. It's going to take an input x. And now what we're doing is we're just giving the output of this as the input to our machine, f of x. And then f of x is then going to give us another output, and this output will be f of g of x. And really there's nothing too special about it. It's just, imagine just f of t, but now t is itself a function. Now, some functions that you've probably often seen before are f of x is equal to mx plus b. Or g of x is equal to ax squared plus bx plus c, the quadratic function. Or h of x is equal to 3x plus 2 for actual numbers rather than just letters. But so far, I know that this is quite abstract. So let's look at a concrete example. Let's say that I'm going to go to the store, and this is going to be the tomato store. I want to buy some tomato cans because who knows, maybe I want to make a pizza. And each of these tomato cans, they are going to be $2 each. And I'm going to buy 5 of these in total. So I'm going to get 5 of these tomato cans. So how much did I spend? I spent $10, right? $10. And, well, what happens if I find out, oh, I didn't buy enough? I'm going to go back and buy another tomato can. Then I got $10 plus $2. In total, I spent $12. But what happens if I just want to find out the amount of money that I spent when I buy any amount of tomato cans? What if instead of buying 10 tomato cans, instead of buying 5, I bought n tomato cans? So if I bought n cans, then that means that I got 2n. I spent 2n money, right? Because there's 2 per can, and then I bought n of those. And this is going to be in itself a function. This is going to be a cost function where we just write cost of n is equal to 2n, which is going to be how much that I spent at the store. We can then just plug n into this processing machine, and from it, I get how much I spent. Again, n could be replaced with x, y, p, q, t. It really doesn't matter. The name of the variable does not matter. Now, functions don't need to be only of one variable. And here you really get to brag to your friends, because functions of more than one variable are very spooky, and they don't get introduced until university. But really, it's quite simple. What if I go to the store and I buy n tomato cans? So, tomato cans, more cans. Let's draw this one a little bit better. I'm going to buy n of these cans, which are all going to be x dollars. So I'm going to buy n of these. Now, how much did I spend now? I spent nx dollars, right? N tomato cans multiplied by x dollars each. And I can write this as its own function, cost, that depends now on 2 things. Cost is going to depend on n and x, and I'm going to get this equal to nx. If x is equal to 2, then I have cost of n2, and I get this to be 2n, which will just be what we had before. Each tomato can cost $2, but now I can actually change my x. What if x is 10? Then I spent 10n, and holy crap, those tomatoes are very expensive. But what if I only bought 5 cans? 5 cans, but I don't know how much they cost. Then I spent 5x. And really, functions can actually be of as many variables as you want. You could have, I could go to the store and I could also buy some peach cans. So these are going to be peach cans, which these are going to be y dollars. I'm going to buy m of these. And I want to find the total amount of money that I spent. Then I now have a cost function, which is going to be dependent on n, x, m, and y, and it's going to be nx plus my dollars. switching between $sign on the left and the right. And really, I know that this is all getting really, really complicated. So getting back to something that everybody knows, because I know that everyone here has used multivariable functions before. Take addition, for example. Addition is really just x plus y, right? Everybody has done addition. 2 plus 3, 4 plus 5. And really, these two numbers on either side can be whatever we want. I could write those as to be any variable, and really it's just x plus y, right? And that in itself is going to be a function, which we call the addition function. Now, this is similar with really anything. We could have multiplication. G of xy, which is just going to be x times y. Or we could have division and really any other operation that you've seen in the past. But enough with that introduction to functions. Let's get into drawing some functions. So, drawing two straight lines perpendicular to one another, we're going to have these two lines, which we label as x and y. Now, we do have to state something here. We have to state that y is equal to f of x, because we want to write f of x is equal to something, and really, we want to be clear of what exactly we're doing. In fact, I could write x equals f of x instead, and that would completely change what I'm doing. So we want to make sure that the reader knows, or even just to make sure that you remember, that y is equal to f of x. And let's say here that f of x is equal to 2x. This is our cost function from before, where x is the number of tomato cans that we bought, and each of them were $2. Now, let's try to imagine, what will this function look like when we try to draw it? Well, we know that it will go through 0, because we know that f of 0 is equal to 0. So it has to go through the point 0, 0. So xy is equal to 0, 0. What other point might it go through? Well, we can also evaluate it at another point. We know that f of 1 is equal to 2. That means that it goes through the point xy is equal to 1, 2. As a result, we can draw another point on the plot. This is going to be 1. This is going to be 2. This is going to be the origin 0. Then all we need to do is we just draw a line through it. We draw a straight line through this. And that gives us our line. And many of you have probably seen this in your classes before. But now we'll get into something a little bit more complex. Now, I'm not going to get into the full curve sketching procedure, because I know that many mathematicians are going to get mad at me by the fact that I only evaluated it at 2 points, and then you just draw a line through it, and that's not going to work for any other functions. So I'm probably going to make another video soon on curve sketching, but really that's going to be in the future, and we don't have enough time to get into that now. So now, let's say that we have a function of more than one variable. So let's say that we have f of xy is equal to x plus y. So this is our addition, right? This is just what happens when we add two numbers. 3 and 5, we add it to get 8, right? And let's say that we want to draw what this looks like. That's going to be odd. What happens if we try to use two axes again? So what happens if we try to use our old Cartesian plane friend? How might we draw that on here? Well, we have an x, we have a y, but here x and y are both what we call independent variables. So it's not really possible to draw it like this, is it? And so we need to do something, a little bit of an optical illusion. We're going to go up a dimension. And we are going to draw a different kind of plot, which will be the three-dimensional plane. So as my monitor, of course, cannot display 3 dimensions, we need to sort of use an optical illusion here. This axis, we're going to use a new letter. We're going to call it Z. And then we're going to draw another axis diagonally. This is going to be called our x-axis. And then another axis here, this will be our y-axis. Now I want you to notice how this, you could call it like a plane, right? Now we need to think in sort of 3 dimensions. So this is going to be a plane. You can think of it as just a piece of paper. A piece of paper on our plot. This will be our old friend Cartesian plane. This will just be the x and y plane. And now we're going to try to use the same method as we used before. We're going to evaluate, we're going to find out what this function is at some values of x and y, and then we're going to try to determine what our function is going to look like in this new plot. So, for example, let's say x is equal to 0 and y equals 0. Then we know that f of 0, 0 is going to be 0. That means that our function is going to go through the origin. Now, I almost forgot. We need to state z is equal to f of xy. To make sure that the watcher or whoever reads our work, or really even makes sure that you yourself remember, we need to remember that this axis right here is going to be representing the value of our function. So this is going to be, it's going to go through the point 0, 0, 0 now. So this is going to be x, y, z rather than just x and y. But evaluating this function one point at a time is going to take forever. As a result, we're going to use a sort of different method. Let's pretend x equals 0. Just x equals 0. Then we have f of 0, y is just equal to y. Now this looks familiar. Let's again remember the name of the variable doesn't matter. We could replace this y with an x, or we could replace this y with a t, but really this is just our linear function, right? This is just g of y is equal to y. And we know what this function looks like. This function, if we draw it out for a y and a g of y, this is just going to be a straight line. It's just going to be a straight line, and it's one of the functions that probably very familiar with. But what does this part mean? When we're told that this is only true, basically we only have this when x is equal to 0. What might that part mean? Well, let's think. On this graph right here, let's erase this. Let's erase these lines. Oh, didn't mean to erase the axis. On this plot right here, where does x equal to 0? Does x equal to 0 here? No, not really. What happens if it's on the y-axis? Does x equal to 0 there? Yeah, I think so. Does x equal to 0 here? Yeah, I think so as well. That's odd. X equals to 0 anywhere here, and x equals to 0 anywhere here. What about if I draw a point here? Does x equal to 0 there? Yeah, I think so. And so x is equal to 0 anywhere in this region. In this piece of paper, that if we put on this three-dimensional plane, if we just put this piece of paper in what we call, this is what we call the YZ plane. The YZ plane, if we put the piece of paper there, x is equal to 0 everywhere. And when we're told that, oh my gosh, when we're told that on this plane, we have this, we basically have this plot, then that means that we can just draw it. We can just pretend that this is this plot in this specific plane, and we can draw this linear function. Now we can do the same thing with x. Now let's pretend this time that y is 0. Then you have f of x 0 is equal to x. This is also a function we know. This is just the linear function. Again, it just looks like this, right? X, g of x. This is going to be what it looks like. And this time, let's ask again, where does y equal to 0? Well, y is equal to 0 here, right? It's on the xz plane. Y is equal to 0 here as well. Y is equal to 0 if I draw this point. Y is equal to 0 there. And this is what we call the xz plane. So now sliding a piece of paper onto our three-dimensional plot, we are going to have this be our another sheet, which will be our xz plane. And here again, we can draw a linear function. Now, we have these two lines that we know both of them belong to this one plot. Now that's odd. That is definitely very odd, doesn't it? Now, we've never seen that before for our one-dimensional plots. So what happened here? Can we still draw a singular line through our points? Well, it almost seems like it, right? I can just follow this line down and then back up. But I can keep doing these types of rules. Rather than y equals 0, oh, that's not supposed to be there. Rather than just y equals 0, I could have y is equal to 1. Then I would have f of x 0, f of x 1 is going to be x plus 1. This is going to be a plot, f of x, g of x is equal to x plus 1. And now we're going to have a different kind of plot. Now we're going to have something that looks like this. It intersects at 1. So this will also belong to our plot. And it seems like we can keep doing this. We can do this for any y. We can do this for y equals square root of 2. We can do this for y is equal to pi. We can do this for anything. So that's odd. And it turns out that instead of drawing just a line, we have to draw a surface. So yes, we call it a surface, but that's honestly, I find that to be a very complex name. So just think of it as like a shape. Here we can basically, what we're going to do to draw this is we're just going to connect these two plots. And then we're going to shade it in. So drawing in three dimensions is quite difficult. So we're not going to draw the entire plane, even though it really extends further out there to really any x and y. But here we just have a plane. So rather than having a single line, we are going to have a shape that connects all of our points. Here, in this case, the shape is going to extend infinitely in every direction. But in many cases, that's also not the case. Now, erasing all of these. Now we could go higher, right? We could go up to 3 variables rather than just 2, f of x, y, z. And we could call our last axis, we could call this W. We're going backwards instead of forwards in the alphabet this time. But unfortunately, my monitor is not four-dimensional, so unfortunately, we cannot draw that. But there is one last thing I want to mention before we end off this first video, which are known as level curves and surfaces. And that sounds fancy, and really, it really isn't. So let's go back to two variables. For example, let's say I have f of xy is equal to x plus y. Back to our addition function. And now let's pretend for a second that f of xy is also equal to some number. Let's say it's equal to 2. Then this is just something that we want to solve, right? 2 is equal to x plus y. Y is equal to 2 minus x. And this looks familiar. We know how to draw this. Going back to our little plane, we can draw this pretty easily. It's just going to have an intercept of 2, and then it's just going to go down. It's going to go down. This is also going to be 2. Now, this is quite interesting, right? So even though this function, this is three-dimensional, and then when we set it equal to a point, we went down a dimension. Now we went back down to 2 dimensions. That's interesting. Where did the other dimension go? And you've actually seen this before. So with any really, back when we had one variable, say f of x is equal to x plus 2. When we set f of x equal to 0, then we get x plus 2 equals 0. We get x is equal to negative 2. This tells us the y-intercept, right? This tells us the point where our function intercepts the y-axis, as here is going to intercept it at negative 2. So in this case, we have a one-dimensional line, and when we set it equal to a number, we went down a dimension. Now we are at dimension 0. Dimension 0 is just a point. When we were in 3 dimensions, or when we had a 2-dimensional plane, or just a shape, we went down a dimension as well. We went down a dimension to a line. Setting f of xy equal to, what was it, 1? Here, 1 is equal to x plus y, y is equal to 1 minus x, right? This is just going to be a line. And what we call this a level curve. So really, you can just think of level curves as just what happens when we take this function and we just set it to a value. We get what we call a level curve. But I also stated something else, didn't I? I called something a level surface. What is that? Let's say we have a function of 3 variables. Let's say it's going to be equal to x squared plus y squared plus z squared. Right? I'm just taking 3 variables and I'm squaring them. Nothing really special. Now, let's pretend that f of x, let's set this equal to a value. Let's say that this is equal to 1. Again, solving our equation, we just get x squared plus y squared plus z squared is equal to 1, right? Because they're both equal to each other. So, how in the world would we draw this? What does this look like? Well, let's think. What happens when x is equal to 1? Now, let's remember, right? When we had a 2-dimensional surface, we went down a dimension and it became a curve. when we had a one-dimensional line and we went down a dimension and it became a point. Here we have 3 dimensions. We have 1, 2, 3 dimensions, right? So it's going to go down 1 and it's going to become a surface. That's odd. So that means that we need to go back to our old friend, the 3-dimensional plane. So we need to pull up the 3-dimensional plane. This is Z, X, and Y. Now let's think. What happens when X is equal to 1? That means that y squared plus z squared, or 1 plus y squared plus z squared is 1. Cancels. You get y squared plus z squared is equal to 0, correct? However, we know how squares work, right? When we take -2 squared, we get 4. When we take -1 squared, we get 1. And really, when I square a number, it can't really be negative. The lowest the square can be is 0 squared is 0, right? So if y was positive, like let's pretend for a second y is positive. That means that y squared would be positive. And that means that the only way for this to be equal to 0 is if z squared was negative. Oh. So if y squared was positive, it means that z squared would be negative. That's not possible. Z squared can't be negative. That means that y and z have to be 0. Now, I know we didn't check the y is negative case. If y is negative, then y squared is still positive, right? When I have any negative number squared, it still becomes positive. -2 squared is 4, -3 squared is 9, right? It always becomes positive. And this means that when x is equal to 1, y and z both have to be 0. Now what happens if x is -1? Now we know 1 squared is -1 squared, so that's not going to change anything. You're still going to get y and z is 0. What happens if y is 1? If y is 1, then we're still going to get, well, this time we're going to get x and z is 0, right? Because if you look at this equation, if we really just take x and take y and we just swap them, then nothing really changes. We could take x, and remember, right? The name of our variable does not matter. We could just take these two and we could just swap them. I could call this axis the y-axis and this axis the x-axis. And nothing really would change. So that's what we call symmetry. We have a symmetry. And that means that when y is 1, this is the case. When y is -1, this is the case. And when z is 1, this is the case. And when z is -1, the same thing happens, right? So that means that we have a couple of points that we know are on this plane, or on our 3-dimensional Cartesian graph. We know that it's going to go through 1, 0, 0, -1, 0, 0, 0, 1, 0, 0, -1, 0, 0, 0, 1, and 0, 0, -1. So we know that these 6 points are going to be on our graph. It's going to have 1 here, 1 here, 1 here, 1 here, 1 here, and 1 there, right? Now, I think a lot of you could probably already guess what we're going to draw. But let's do one last thing. Let's pretend that z is equal to some number. What's a good number? Let's say that z is equal to 0.5, right? Just pretend that z is 0.5 for a second. Then x squared plus y squared plus 0.5 squared is 1. We're going to move this to the other side. x squared plus y squared is equal to, what's 0.5 squared? 0.5 squared is just 1/2 times 1/2. It's going to be 1/4, right? So it's just going to be 1 minus 0.25. This can be x squared plus y squared is equal to 0.75. Now, for those who have studied it, I'm sure this might look a bit familiar. X squared plus y squared is 0.75. And if it doesn't look familiar, what happens if I write it a little bit differently? I'm going to write it as the square root of 0.75 squared. What happens if I let this be a variable? I'm going to let a variable conveniently labeled r, right? I'm going to let r be equal to 0.75. Then x squared plus y squared is equal to r squared. And for those who have studied it, this is exactly the equation for a circle. So that means that there's going to be a circle. There's going to be a circle somewhere in this graph, right? There has to be a circle somewhere. We just found that there's a circle. And we found that there's a circle when z is equal to 0.5. So where does z equal to 0.5? Let's think. Where on this graph does z equal to 0.5? Well, we know z equals 0.5 here. This is 0.5. Is z equal to 0.5? Is z equal to 0.5 there? Yeah, I would think so. What about here? What about there? There? Z is equal to 0.5 anywhere. And z is equal to 0.5 in this little sheet. Okay, I deleted a lot of my axes. Z is equal to 0.5 on a lot of these points on this sheet of paper that sort of lies, you can think of this piece of paper that sort of lies parallel to the xy plane, right? And there's going to be a circle there. So there is going to be a bit of a circle here. There's going to be a circle here around it. Now we know that a negative number squared is equal to the same number squared, right? Because negative 1 squared is just positive 1. So that means we're also going to have the same thing at negative z, because we're just going to be doing the exact same computations. And I think here you can begin to understand what we're going to draw. We know that all of these points are going to be on our surface. And it turns out that this is going to be a sphere. So this right here is going to be the equation for a sphere. So this graph right here, this formula, setting this equal to 1, gives us a sphere. So even though we couldn't draw this 4-dimensional function, we can still evaluate it at a certain value, and we're going to get a sphere. All right. So let's wrap up now. Now, we don't have time to get into every possible function. I will go into some of the next videos expecting you to know some of the common functions like square root of x, x squared, x cubed, 2x, or 2 to the x, e to the x, log x, and a lot of the trigonometric functions like sine x, cos x, and log x. So if you haven't gotten to learn those types of functions yet, I recommend you to check out some videos that I will link in the description. Oh my gosh. I will link in the description, and in the future I will likely make some videos to cover them. Also, rest assured that learning every function here is not actually too necessary for calculus. Now, don't get me wrong, of course it is nice to know to just be able to draw these functions on these graphs and really get an understanding of how they work, but really it's not actually too important. But I believe that that concludes this video today, or that concludes this video today. So today we discussed functions, we discussed single variable, multivariable functions, and the basics of drawing them.